Welcome back. We're going to do another example of how to determine the structure of an organic molecule. And we're going to use, yet again, the mass spectra, the IR, the proton NMR, and the carbon NMR spectra all together. We first start with the mass spectra to figure out the chemical formula of the compound. Now the peak that's farthest to the right of highest abundance falls at a value of 85 grams, and this is out of 100%. The mass that is 1 unit above it, so at 86, or a mass of 86, that only has a percentage abundance of 4.5%. The tallest peak that falls farthest on the spectrum is your M plus peak, and because it's already at 100%, we do not need to recalibrate it to bring it back to 100, and because we do not need to recalibrate it, then the M plus 1 peak is going to be exactly what's given in the spectrum, in other words 4.5%. Now to figure out how many carbons this molecule contains, we divide the percentage of the M plus 1 peak, so long as the M plus peak is out of 100, we divide this value by 1.1. So 4.5 divided by 1.1 is about 4. And that means that if you do have 4 carbons in the structure, well, since each one of the most abundant isotopes of carbon is carbon 12, you're going to account for only a mass of 48 grams. If we subtract 48 from the original mass of 85, we're going to find out that the residual mass is 37. And you might be tempted to say, well, okay, so we have 37 hydrogens on this molecule, so it's C4H37, except that you can't, because an alkane can have at most 2n plus 2 hydrogens, where n is the number of carbons. Since we have 4 carbons, at most we could have 10 hydrogens in this molecule. So needless to say, we are missing some elements that account for this discrepancy in the mass. So what you might want to pay attention is the value, the mass value of the M plus peak, because it happens to be an odd number. And because it's an odd number, this means that you have to have an odd number of nitrogens. On the other hand, if the number would have been an even value, then you would have had to have an even value of nitrogens, where 0 also counts as being even. But here, because the value is odd for M plus, we have to have at the very least 1 nitrogen. That's not negotiable. There has to be nitrogen. So the odd number of the M plus peak corresponds to the odd number of nitrogens in the structure. So we're going to introduce 1 nitrogen, and we're going to see what happens to the formula. Now nitrogen, the most stable isotope of this element is nitrogen 14. So if we subtract 14 from the mass, now we have 23. Now 23 hydrogens is still too many hydrogens to fit in this molecule. So this tells us that we're missing at least another element. Now you might be tempted to say, okay, well, let's add more nitrogen. Like let's add, a second hydrogen, or no hydrogen, excuse me. Let's add a second nitrogen to this formula. And that would actually be a very erroneous thing to perform here, because if you do that, you'll be invalidating the rule, which says that if you do have an odd number for the M plus peak, as far as the mass goes, then you must have an odd number of nitrogens. So we cannot have 2 nitrogens. We either have 1, or we have 3, or we have 5. But if we were to increase the value of nitrogen to 3, well, since each one of them is 14, 14 times 3 will equal a total of 42. And so that might be a bit too much to deal with. In fact, 42 will basically be way above the value that we have here for the hydrogen. So we will go past the actual mass we have. So that doesn't even work. Even if you tried it, it will not work. Your mass will be completely off. So then the only other choice in the absence of an M plus 2 peak is for you to have oxygen. So we're going to introduce, right, so we cannot do more nitrogens because we go past the mass, the allocated mass. So we're going to introduce oxygen, right, because this is the only other element that even if you don't have an M plus 2 peak, you can add to the formula to adjust for the mass. And here there's no restrictions. You could have 1 oxygen, 2 oxygens, 3 oxygens, as many as the mass, the original M plus mass, requires. So let's add 1 oxygen to this formula. Now this will bring with it a mass of 16. So if we subtract 16 from the original, now we're going to end up with an overall mass of 7. And having 7 hydrogens in 4 carbons is absolutely okay. That we can make happen. So we can place 7 hydrogens, and with this information we now know the formula of this molecule. If this is a little bit foreign of a concept to you, I recommend that you look under the description, the link for the mass spectral lectures that present you with all the data, right? So if you need to review that, I recommend you review it. Right now, I'm just going to go in somewhat fast through this procedure. All right, but now we know that the formula is C4H7NO. Let's determine the index of hydrogen deficiency to see what kind of choices we have. So looking at carbon, we have 4 carbons. We already talked about the idea of the 2n plus 2 rule for the alkanes, which tells us that we have a total of 10 hydrogens, right? So 2 times 4 is 8 plus 2 is 10. And as far as the equivalent hydrogens, well, every hydrogen that's in the structure we count, right? So there's 7 hydrogens, hence the fact that I have a 7 here, but there's also a nitrogen present. And the nitrogen basically subtracts 1 hydrogen for every nitrogen that you have there. So 1 nitrogen present in the molecule means that we're going to subtract 1 out of the total of hydrogens we have there. Now oxygen, we do nothing with that. We simply ignore it. So we have 2 times 4 plus 2, all of that minus 7 minus 1, which is the same thing as saying 10 minus 6, which is 4, and 4 divided by 2 is simply 2. So this is telling us that the structure could have any of the possibilities presented here. You could have 2 double bonds, or you could have 2 rings, or you could have 1 ring and a double bond, or alternatively you could have a triple bond. These are all the possibilities that an IHD of 2 represents. And needless to say, that's a lot of possibilities, right? So this isn't necessarily narrowing things down, but we have an idea of what might be there. All right, so this is the other complication too. Because you do have heteroatoms, you have to kind of consider the idea that perhaps if you do have double bonds, the double bonds could be between carbon and the heteroatom. So carbonyls are a possibility as well. All right, so let's go to the IR with this information and see if we can make something up that's a little bit more detailed and a little bit more helpful. All right, so here are the options: 2 double bonds, or 2 rings, or 1 ring and a double bond, or a triple bond. And here's the formula. All right, so one thing to notice is that there is a very prominent peak, very strong peak that falls pretty much at 1700 in the IR spectrum. And what this is representing is a carbonyl bond. All right, so this is what I was just implying a little earlier. When you do have heteroatoms, if the IHD is not 0, then there is a chance that you could have a multiple bond between carbon and the heteroatom. Okay. Now the other thing to notice is that typically when you do have carbonyls, the carbonyls fall between 1720, 1730, in some cases 1760. Yet this particular carbonyl is redshifted, it's down to 1700. And you may recall from the IR lecture, and in case you don't, look at the link in the description below to kind of revisit those topics for IR. But you may recall that when you're in this region, and even, getting into the 1600 region, you do have a specific carbonyl compound that can make this happen, and that's your amide. The amide, or even the carboxylic acid, but notice because of the structure, the idea of a carboxylic acid is mute. You can't have a carboxylic acid if you do not have 2 oxygens. But an amide, it's absolutely fine because you do have oxygen and nitrogen, which is what you need to make an amide. So this is kind of looking potentially like that. Now, another feature to notice in this spectrum is that above 3000 you do have a peak, but not just any kind of peak. You have a broad peak. And this particular broad peak is representative of a hydrogen that's bound to an electronegative element such as nitrogen. So what this is now telling us is that we probably have an amide present in this molecule, and not only that, the amide is going to have at least one H, maybe two. In fact, if you look at the peaks right here, you have two separate peaks broad in scope above 3000, which could represent that there is two hydrogens present on that nitrogen. All right, now another thing that I want to highlight too is that there is no peaks in the region that where you would expect to see triple bonds, right? So in that 2200 region, there's virtually nothing, which corroborates the idea that, okay, there is not going to be any triple bonds. And that's a good thing, right? Because if we already have a carbonyl, we can't have a triple bond because it's either a triple bond or a combo of double bonds, but you cannot have triple bond and double bond because that will give you an IHD of 3. All right, the other thing too is that if you look a little bit lower than 1700, there is no other peaks that show up, which means that it looks like this doesn't have a carbon-carbon double bond. You do have the carbon-oxygen double bond, but it doesn't look like you have an alkene in here. All right, so if you have no alkene and you have no alkyne or triple bond for that matter, then the possibilities right here really break down to only one thing. Oh, and one more thing that I want to highlight, because since we have a carbonyl, we do need to look at this possibility. Between 28 and 2600, if you do have two peaks that show up, that's indicative of an aldehyde, but we don't see anything showing up between 26 and 2800, so there's no aldehyde here, which is further proof that most likely not we have an amide in here. All right, so really the only possibility that we have is that this structure, since it's not going to have an alkene, but it has to have the carbonyl bond, must have a ring and a double bond in association with this. So that's kind of important because now we're really narrowing down what this could be. All right, so we're going to have a cyclic amide with at least a nitrogen hydrogen bond present. Okay, so that's what we know from the IR spectrum. So it's time to look at a few possibilities. Now, here is where you kind of have to be a little bit flexible, because sometimes the best approach may be to just go directly to the NMR and then gather more data from there. Other times, if you don't have a lot of possibilities to draw, you could try to draw a few isomers that fit the profile for the IHD number you've calculated, the chemical formula that you've determined, and the functional group features that you have identified in the IR spectrum. So if we are saying that we're going to have a cyclic molecule, so a ring structure, one of them could be a cyclic structure where you have the 4 carbons, so 1, 2, 3, and 4, along with the nitrogen making up the cyclic portion of this molecule. Now, you still have to keep that amide functionality, so notice that you have carbonyl, and to the carbonyl you have the nitrogen bound to it. To that nitrogen, we have a hydrogen present on it, which is, corroborating what we saw in the IR spectrum. Okay, so I have an amide, we have a hydrogen bound to that nitrogen, so this is looking okay in that respect. And now another possibility would be to turn this ring smaller, right? So go from a 5-member ring to a 4-member ring. And one possibility would be to take one of those carbons out of the ring portion. You get your 4-member ring right here, but the fourth carbon will now be sticking out, and it could be sticking out exactly opposite of where the nitrogen is bound, or it could be right next to it, right? So these are the two possibilities you have, not counting the possible enantiomers that you may have. All right, now the other option is to, oh, and by the way, having the methyl group bound to the nitrogen is not an option, because that would get you rid of the nitrogen hydrogen bond present in these structures, and then that will invalidate what we saw in the infrared spectrum. So that's not a possibility that we want to go with. So we continue making the ring smaller, and this time around we have to go to a 3-member ring. So one way to make this happen is to make them all carbon, so the 4th carbon will be outside. That's where your carbonyl potentially could be present. And since this is got to be an amide, we're going to have the nitrogen bound to it. And the last possibility will be to still have a 3-member ring, but the nitrogen is part of the 3-member ring, And since this has to be an amide, that particular carbon needs to be a carbonyl carbon. And then the other two carbons need to be outside of the ring structure. And once again, they cannot be bound to the nitrogen because otherwise you will end up with no NH bond present. Okay, so these are all the possibilities that you can really draw. I really can't think of any other one that fits the descriptions from the chemical formula, the IHD value, and the IR spectrum. Now, in some cases, however, it might not be this easy. If you want to start drawing all the possibilities for the isomers, by the time you get to this point, you may have so many options that this may be not the best way to approach the problem. But right here, we only have 5 possibilities, which is the reason why I decided to draw them before tackling the NMR. But just be aware that sometimes you're going to have so many more possibilities for the molecule you're investigating that that will be a little bit detrimental to you solving the problem in a timely manner. All right, so we're going to take those 5 possibilities and we're going to start looking at the carbon and the proton NMR to make some judgment calls. All right, so once more, the formula contains 4 carbons, and what you'll notice in the carbon NMR is that there are 4 separate peaks, meaning that all 4 carbons are inequivalent with each other. They are not the same type of carbon. So we're going to have low symmetry in this molecule. The other thing too, which corroborates what we saw in the infrared spectrum, is the fact that we see a peak at about 180, which is indicative of a carbonyl carbon peak. And the other thing too is that if this was very close to 200, then that would be indicative of an aldehyde. We know from the IR spectrum that there is no aldehyde, so it's also good to see that the carbon NMR also corroborates that. All right, so this is looking okay so far. We have a carbonyl carbon. It's definitely not an aldehyde carbon, but it's kind of high up in there. All right, so 4 different carbons. Okay, that's the thing to keep in mind. All right, so now let's look at the structures again and see if we can kind of rule out a few of them. All right, so what you'll notice for the structure on the left side is that you do have 4 different carbons. This is a carbonyl carbon with no H's. This is a CH2, that's a CH2, and that's a CH2. But the difference is that this CH2 is bound to a carbonyl carbon. This CH2 is bound to a nitrogen. And this CH2 is only bound to carbons. So all 3 of those CH2s are actually different electronically speaking from each other, so they're all inequivalent. So this structure is a good possibility still. All right, let's take a look at the one right there. Carbonyl carbon is unique. The carbon with 1H is unique. The CH2 is unique, and the CH3 is also unique. So all 4 of those guys are inequivalent. So this also works out with the carbon NMR. Same thing goes for this structure. Carbonyl carbon is unique, CH2 is unique, CH is unique, CH3 is unique. So you have 4 inequivalent carbons. Looking at the structure with the cyclopropane functionality, you'll notice that you have carbonyl carbon, which is unique, CH is unique, but then this CH2 and that CH2 are identical to each other. They're both bound to the CH and they're both bound to another CH2, right? So they are the same. All right, so what this tells us is that this molecule is no longer an option, right? Because we have to have 4 inequivalent carbons, and this does not have 4 inequivalent carbons, so it's out the door. We eliminated it. And then we look at the final one right here. Well, carbonyl carbon is unique, quaternary carbon is unique, but then you have CH3 and CH3, which are the same as each other. So you only have 3 inequivalent carbons, meaning that this structure is also gone. It's no longer an option. All right, so we've narrowed it down to 3 possibilities for the structure. It's time to look at the proton NMR. Okay, so here we go. This is the proton NMR, and we're going to bring back the 3 possibilities to which we've narrowed it down. All right, so let's take a look at the spectrum. What I want you to notice is that you have 4 different peaks because there's 4 different kinds of protons in the structure. Okay, but the other thing too is the integrations. Notice that this broad peak that falls between 7 and 8 integrates to 1 proton. Now here I want to make a point. The fact that this falls between 7 and 8 may make you think that you have an aromatic compound. But there's 2 things that will tell you that this can't really be an aromatic compound. The first one is that the peak is actually pretty broad, and generally speaking, the aromatic peaks, they might be multiplets, they might show a lot of splitting, but they rarely ever show up as broad peaks. And the second one, which is perhaps the most important part of it, is that for you to have an aromatic ring, you have to have six carbons in total, and 6 carbons you do not have. So this is not an aromatic peak. Another way to tell that this cannot be the case is because of the IHD value. For you to have a benzene ring in your structure, the IHD value has to be at least 4, and the IHD was barely 2, so you cannot have a benzene ring. Once more, if you need further guidance, look at the link below for the mass spec, and you'll find the discussion of IHDs. All right, so looking at the integration, we have one proton. This broad proton is actually the NH peak, okay, which all three of these structures contain, and it falls really far downfield because of the fact that it's bound to an electronegative element and the fact that you have resonance withdrawing electron density from the hydrogen. All right, but what about the other peaks? Well, you have a triplet that integrates to 2 H's, another triplet that integrates to 2 H's, and then you have a multiplet that also integrates to 2 H's. Okay, so let's take a look at the possibilities. All right, so we know that this carbon only contains 1 H, this one contains 3 H's, and this contains 2 H's. Well, right out of the gate, this doesn't work because we know that the 3 peaks here have to have 2 hydrogens each. This integrates to 2, 2, and 2. So you should have a CH2, a CH2, and a CH2, all different from each other. This doesn't fit the bill, so it's gone. Similarly, this structure has a CH2 down here, but over there we have a CH and a CH3. So this doesn't work. 3 hydrogens, 1 hydrogen, 2 hydrogens, this cannot be the structure. However, the 5-member ring that we have here, you will notice that it contains a CH2 next to another CH2 next to another CH2. And we already said that all 3 of those carbons are inequivalent, so those hydrogens are also going to be inequivalent. And check this out. These 2 hydrogens are next to 2 hydrogens, so they're going to be split into a triplet. And what we see here is a triplet. These 2 other hydrogens are next to a carbon with 2 H's, so they're going to be split into a triplet as well. All right, that's what we see. And then these 2 hydrogens are next to a carbon with 2 H's, and then another carbon with 2 H's, and these 2 guys are not equivalent, so we end up with a multiplet. All right, so everything that we've seen in the mass spec, the IHD, the IR, the carbon NMR, and the proton NMR points to the fact that the structure is 2-pyrrolidone, shown right here as the cyclic compound. So this is another method of approaching these molecules, and hopefully this gives you an idea of how to approach this type of problems. Um, so with that being said, I hope this helps, and I'll see you next time. Bye bye.